Welcome, focused learners, to this explainer of our source material. Today, we're diving straight into the invisible, ultimate opposing forces of nature, acids and bases. We're going to explore how these two completely contrasting types of chemicals are essentially locked in this constant dynamic struggle. They are always striving for balance, whether it's right inside our own bodies, out in our environment, or scaling all the way up to our biggest global industries. So think about this for a second. What on earth do a painful bee sting, a heavy car battery, and a delicious, fluffy baked cake actually have in common? I know, it sounds like a weird riddle, right? But the answer literally lies in the invisible chemical rules that we are about to decode together. All right, let's jump right into this. Here is our roadmap for the explainer. 1. The Chemical Balancing Act. 2. Acids and bases every day. 3. The rules of the game. 4. Neutralization and buffers. And 5. Your future in chemistry.
Okay, starting off with Section 1, the Chemical Balancing Act.
I want you to go ahead and imagine these chemicals as two rival sports teams playing a continuous, high-stakes game of balance, pulling our physical world into totally different directions. Here is the basic scouting report. On one side, we have acids. If you encounter them, they typically have this sharp, sour taste, and chemically speaking, they react pretty aggressively with certain metals. On the opposing side, we have bases. These guys often feel slippery to the touch, and they are absolutely fantastic at breaking down stubborn oils and greases. Now, when these two contrasting forces finally clash, they naturally just want to neutralize each other. They'll basically fight until they hit a state of absolute calm.
Moving right along to Section 2, acids and bases every day.
Let's pull these abstract concepts out of the lab and put them right into the tangible world around us. Because these chemical properties literally dictate your daily routines. You know that sharp tang in your morning coffee or orange juice? Yep, that's acid. Got indigestion? You grab a basic antacid to neutralize it. Even when you're cleaning up, the soap that's dissolving the grease on your hands is a base. From the natural rainwater falling outside to the intense sulfuric acid powering your car's battery, the whole shebang relies on this chemical duality. Which brings us to Section 3, the rules of the game. Now that we see just how widespread this all is, let's zoom in on the microscopic rules actually governing these interactions. We'll start with the foundational framework, the Arrhenius concept. Now, this is the classic, water-based definition you will find in every single physical chemistry textbook. It simply states that acids release hydrogen ions, that's H+, when they are mixed into water. Conversely, bases release hydroxide ions, or OH-. Now, what's really interesting about this is how it plays out in reality. Picture yourself drinking lemonade at a summer picnic. The lemon juice mixes into the water, and the citric acid dissociates. It literally floods your drink with those H+ ions we were just talking about. Your taste buds are biologically hardwired to detect those exact hydrogen ions, instantly firing signals to your brain that just scream sour. And, the higher that H+ concentration gets, the more your face is going to pucker. But of course, science evolves. The rules got expanded by Bronsted and Lowry because they realized, hey, water isn't strictly required for these reactions to actually happen. Instead, they defined acids simply as proton donors, again, looking at that H+, and bases as proton acceptors. It's all about the handoff, the transfer of the proton from one chemical to another. To really visualize this proton transfer, think about that ammonia-based glass cleaner sitting under your sink. When you spray down a bathroom mirror, the ammonia is acting as a Bronsted-Lowry base. It actively reaches out and accepts a proton from the invisible moisture sitting on the glass. This specific microscopic chemical interaction is the magic secret behind its ability to cut right through your oily fingerprints without leaving a single streak behind. Finally, we reach the absolute broadest rule of the game, the Lewis concept. So the crucial point here is that we aren't just tracking protons anymore. Now, it's entirely about the movement of electron pairs. Under this rule, a Lewis acid accepts a pair of electrons and a Lewis donates a pair. Now, if electron pair theory sounds a bit dry, just look at how it drives modern engineering. Think about the millions of cars cruising down the highway. Their exhaust systems use catalytic converters packed with transition metals, and those metals act exactly as Lewis acids. They accept electron pairs from incredibly toxic exhaust gases like carbon monoxide, binding them straight to the catalyst surface so they can be safely broken down. This tiny microscopic electron dance, it is literally the backbone of Industry 4.0 environmental standards. Pretty cool, right? All right, let's move into Section 4, neutralization and buffers. Here, we are going to tackle the mathematical metrics and the balancing mechanics that keep these opposing teams from just completely wreaking havoc on our bodies and the environment. First up is the neutralization reaction. This is the ultimate tie game scenario. When an acid and a base react, their opposing properties cancel each other out completely. The end result, they form a salt and water. It's a state of perfect chemical calm. And this exact neutralization reaction is what secures our global food supply. Farmers are constantly out there testing their agricultural soil. If heavy rains or maybe overusing fertilizer makes the soil way too acidic, the crops will simply die. So, what's the solution? The farmers spread a base, like crushed limestone, right over the fields. The acid and the base neutralize, forming completely harmless salts and water, which immediately restores that soil to a nutrient-rich state for sustainable farming. Now, to actually measure all of this shifting balance, scientists use the pH scale, and I really want to slow down here for a second to emphasize a specific multiplier, 100 times. The pH scale is logarithmic. What that means is, a drop from a neutral 7.0 down to a 5.0 doesn't just mean the substance got slightly more acidic. Nope, because it moved 2 whole numbers down that logarithmic scale, it is a staggering 100 times more acidic. Let's connect that dramatic math to a real-world scenario. Imagine an environmental scientist out there doing a pond eco-audit. Healthy aquatic life loves and thrives near a neutral pH of 7.0. But if industrial runoff from a nearby factory drops that pond to a 5.0, that water is suddenly 100 times more acidic. That kind of rapid chemical shock severely disrupts the local biodiversity. It is very often a literal matter of life or death for those fish populations. Precise pH balance is absolutely vital. Because sudden shifts in pH are so incredibly destructive, nature actually built in a brilliant defense mechanism: buffer solutions. Think of a buffer as the ultimate chemical shock absorber. It's a specially mixed solution that stubbornly resists any changes to its pH, even if you dump small amounts of a new acid or base right into it. Let's walk through how this happens right now, inside your own body. Step 1, you are playing in an intense sports match, and your working muscles start creating lactic acid. Step 2, that acid dumps directly into your bloodstream. Step 3, your blood's built-in bicarbonate buffer system springs right into action, acting like a giant chemical sponge to absorb that excess acid. And step 4, your blood safely maintains its strict 7.4 pH. And this brilliantly illustrates the incredible power of internal homeostasis. Without that chemical shock absorber, a simple sprint across a field could literally be fatal. Which leads us perfectly into our final segment, Section 5, your future in chemistry. Let's focus entirely on how you can leverage this invisible chemical blueprint for your own personal success. If you're prepping for highly competitive entrance exams, think IIJJ, NEET, BITSAT, ISAR, or NEST, mastering acids and bases is absolutely non-negotiable. Examiners rarely just ask for simple textbook definitions anymore. Instead, they demand that you navigate high-weightage numerical problems. You've got to be able to mathematically calculate the pH of complex buffer mixtures, predict the exact outcomes of titrations, and really understand those intricate shifts in chemical equilibrium based on these foundational rules. But look, mastering this chemical duality gives you a toolkit that extends way, way beyond the exam hall. Whether your goal is to be a medical professional keeping human physiology in balance, an environmental scientist saving our global soil, or maybe an engineer designing next-gen battery tech, these concepts are your rock-solid foundation. You are literally preparing to lead innovations in massive emerging fields like the circular economy, green finance, and sustainable technology. So, I'm going to leave you with this final thought to ponder. Now that you understand the microscopic push and pull that's happening inside your morning coffee, inside your car's engine, and flowing right through your own bloodstream, how will you use the invisible rules of acids and bases to shape our world's sustainable future? Thank you so much for joining me in this explainer of the source material. Go out there and keep looking at the chemistry of your everyday world with totally fresh eyes.